the uh, 10th problem solving session for the course Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. Um, so last week we have covered a couple of problems related to FRIT and the fluorescence quenching. So this week we'll be having a couple of problems related to fluorescent lifetimes and how the ways, the methods by which we measure fluorescence lifetime, and an application-based question, which says it all about how we can study any particular things, uh, some real problems. How we can study some real problems using fluorescence spectroscopy, what methods we can use, um, what sort of measurements that you will take, things like that. So let's start with the first question, which is to calculate the fluorescence lifetime of fluorescent lifetime. So dancyl chloride, which absorbs up maximally at 330 nanometer and fluoresces maximally at 510 nanometer, can also be used to label amino acids in fluorescence microscopy and FRIT studies. And tabulated here are is the variation of the fluorescence intensity in aqueous solution of dancyl chloride with time after excitation by a short laser, and the ratio of intensities is equal to the ratio of rates of photon emission. So calculate the observed fluorescent lifetime of dancyl chloride with water in water. So the given here is IF by I0. So we know that Yeah. So we know that the fluorescent decay follows first order kinetics, where I of t is equal to I 0 exp minus t by tau, where tau is fluorescence lifetime. Sorry, I hope you are able to hear me. Am I audible? I hope you are able to. Yeah, thanks so much. So, yeah, so we are at the first question. So we have been given, um, we have been asked to find what is the fluorescence lifetime of dancyl chloride in water, and at different time points, what are the IF by I0, which is like intensity at a particular time, I of t. So this corresponds to I of t by I of 0. So whatever is given is I of t by I of 0, and we have been asked to find what is the fluorescence lifetime. So fluorescent decay in general, fluorescent decay follows first order kinetics. So that's why the equation for fluorescent intensity at a time t is equal to I0 exp e raised to minus t by tau. And we can write from this, we can write I of t divided by I of 0 is equal to exp minus t by tau. And if you plot I t versus I of t by I of 0, you will get an exponential decay, where this decay, the rate of decay is equal to 1 by lifetime, which is tau. Okay. So what I had done is I had just plotted t as a function of I of t by I0, which is you can see that it has been tabulated here. Time at every time point, the I of t, the fluorescence intensity divided by I0 at time 0 is also given here. So I have plotted that. I think there is some delay. So this is where it is. So this is t nanoseconds, and this is IFT divided by IFC, right? So this is the equation that it is fitting to. When I fitted the data points to a exponential function, I got an equation like y is equal to 0.922 e raised to minus 0.145. Okay, there is a problem with this fitting because you are supposed to fit it to y is equal to e raised to minus point some x. So that's a problem with that. Let me quickly fix that and let you know what is the right. Yeah, I'm sorry, I won't be able to fit it to. Yeah, the plot is slightly wrong because this is we are supposed to fit it without a pre-exponential factor because we don't have a. Yeah, we are not supposed to. So we are supposed to get the fit it to a equation like e raised to minus some particular number, which is the decay rate. For example, I'm giving something like 0.25x. We are supposed to fit it to something like this. I of t by I 0 t. Yeah. Yeah, so this is something which is quite this is how you're supposed to fit it. I couldn't fit the equation to fit the data points to an equation of this sort using the Excel. If I didn't think about it while I was fitting it, I should have thought about it a little bit more because yeah, if we have gotten an equation in this particular way, we will be able to extract out the fluorescent lifetime. Consider that the exponential decay rate is 0.145 nanosecond inverse. We have to find what is the fluorescence lifetime. You can try to fit with these data points to a equation of this particular type. Maybe I'll highlight it. Yeah. So y is equal to e raised to minus. This is just an arbitrary value. This 0.25 is just an this 0.25 is just an arbitrary value. You are supposed to use something which is whatever value that you have quoted after the fitting. So I'm just considering it is 0.145 as per the fitted value gives us from this particular chart in this particular graph. So I'm just assuming that it is correct. This is not the correct answer, but I'm just assuming it is correct and going forward with the following steps. When you can try it by yourself by fitting into equation like this itself and get the correct decay rate and get the correct fluorescence lifetime. Yeah. So fluorescent lifetime is 1 divided by decay rate. So this is equal to 1 divided by 0.145 nanoseconds second inverse. So this is equal to 1 divided by 0.145, which is 6.89 nanoseconds. So which is sort of true if you look at the plot here. So if you look at the plot here, you can see that it starts somewhere at 0.45 and it decays to something like 0.045, right? So somewhere around, yeah, it's somewhere around some 6 to 7 nanoseconds. It comes, yeah, it comes somewhere to 0.3, right? Yeah, you can see that it comes somewhere 0.3. So this is sort of the fluorescence lifetime that we are seeing is sort of correct, and yeah, it should. And if you look at the second part of the question, we have been asked to find what is the fluorescent quantum yield of dancyl chloride in water. The fluorescence quantum yield of dancyl chloride in water is zero point 0.7, and what is the fluorescence rate constant? And we know how to address this question. We have found out previously what is the fluorescence rate constant if given the fluorescent quantum yield and the fluorescent lifetime. So the equation connects these things are, so the quantum yield is phi f is equal to kf into tau 0, where kf is the fluorescence rate constant and we have been asked to find what is the fluorescence fluorescence rate constant, right? So kf is equal to phi f divided by tau 0, and we know that phi f is zero point 0.7 divided by tau 0 for fluorescence lifetime is equal to 6.8789 nanoseconds, which is equal to 6.89 into 10 to the power minus 9 seconds. So this is 6.89 into 10 to the power minus 9. So 0.7 divided by 6.89 is equal to 0.101 into 10 to the power 9 second inverse. Sorry, second inverse. So kf is equal to 1.01 into 10 to the power 8 second inverse. So the fluorescence decay rate can be is found to be 1.01 into 10 to the power 8 second inverse for a lifetime of 6.89 nanoseconds. You have to exactly calculate how the decay rate of this exponential equation, this particular um, exponentially decaying data set. Here I haven't fitted it correctly because the equation is supposed to be in this particular format where y is equal to e raised to minus 0.25, which is the decay rate. 0.25 is an arbitrary number. You have to fit the equation, fit the data points correctly to an exponential decay function to get the correct decay rate. Here I couldn't, I had fitted it to a wrong equation which gives us a wrong decay rate. Yeah, please try it by yourselves to get the correct decay rate. The data points have been given in the slide. The slide before. Okay. Yeah. So the second question is something which relates FRET and the lifetimes of a molecule with and without of the donor molecule with and without without fret happening in that particular system. So in a light harvesting complexes, the fluorescence of a chlorophyll molecule is quenched by nearby chlorophyll molecules. You know that chlorophyll molecules sort of like arranged in a particular pattern in chloroforms, and these molecules are inherently, so this is sort of like the fluorophores, it's chloroforms, and the chlorophyll molecules are arranged in some particular pattern over the uh, chloroform, and you can see that um, these molecules are fluorescent. These molecules are fluorescent, and so because there are like fluorescent molecules sort of uh, uh, which can in turn take up the energy once it's excited because of the light. There can be a potential fret happening in these sort of closely spaced fluorescent molecules. So, given that for a pair of chlorophyll in chlorophyll A molecules, so there are different types of chlorophylls and attached to chloroforms. So one of it is chlorophyll A. So a pair of chlorophyll molecules have a Froster distance of 5.6 nanometer. By what distance should two chlorophyll A molecules separated to shorten the fluorescence lifetime from 1 nanoseconds to 10 picoseconds? So what happens in this particular case? So we can see that fret efficiency E is equal to 1 minus tau dA divided by tau B, where tau dA is the fluorescence lifetime. Fluorescence lifetime in presence of acceptor. Tau D is the fluorescence lifetime in the absence of acceptor. Okay, and what we have to do is, once we find the fluorescence intensity from these fluorescence lifetimes, we can calculate what is the distance between the fluorescent molecule, because we have another equation which correlates the fluorescence efficiency with the distance between the molecule given the Froster distance of a pair of chlorophyll A molecules. So uh, it follows, so E is equal to R0 raised to 6 divided by R raised to 6 plus R0 raised to 6, where R0 is the Froster distance and R is the distance between chlorophyll A molecules. Okay, so tau D, so tau dA is equal to 10 picoseconds and tau D is equal to 1 nanoseconds, and E is equal to tau D is 10 picoseconds is the fluorescent lifetime when it has a nearby chlorophyll molecules. So E is equal to the Fred efficiency in that particular case. E is equal to 1 minus tau Ta, which is 10 picoseconds divided by 1 nanosecond. 1 picoseconds is yeah. So it's going to be 1 minus 1000. So 1 pico. 1 picoseconds is 10 into 10 to the power minus 12 seconds. So 1 nanoseconds is 1 into 10 to the power 1 nanoseconds is 10 to the power minus 9 seconds. So this is equal to 1 minus 10 to 10 to the power minus 12 divided by 1 into 10 to the power minus 9. So this is going to be 1 minus 10 raised to 10 raised to minus 11 divided by 10 raised to minus 9. This is equal to 1 minus 10 to the power 10 raised to minus 11 divided by 10 raised to minus 9 is equal to 10 raised to minus 2. So this is 1 minus 0.01. So this is equal to 1 minus 1 minus 0.01. So this is equal to 0.99. So the Fred efficiency is 0.99 when the when we have given the fluorescence lifetime in the presence of the Fred is 10 nanoseconds, and in the absence for just the donor, the fluorescence intensity is fluorescence lifetime is 1 nanoseconds, and this is the Fred efficiency. Now we have to correlate it to the distance between the donor and the acceptor. So let me just insert one more slide. So this is where we have found what is the Fred efficiency for this closely spaced chlorophyll molecules given its fluorescent lifetime with and without the acceptor molecule next to it. And we've been given what is the frosted distance. So if we know E is equal to 0.99, E is equal to R0 raised to 6 divided by R0 raised to 6 plus R raised to 6, and we have to find what is the R. So we can find R is 1 by E is equal to R 1. I'm just taking the reciprocal on either sides. So 1 by E is equal to R0 raised to 6 plus R raised to 6 divided by R0 raised to 6. This is equal to 1 minus R raised to 6 by R0. 1 plus, sorry, R0 raised to 6. So R raised to 6, R0 raised to 6. I'm just taking the 1 to the other side, which is 1 by E minus 1. So this will tell us R is equal to R raised to 6 is equal to 1 by E minus 1, R0 raised to 6, which implies R is equal to 1 by E minus 1 R0. This raised to 1 by 6. So in our case, R is equal to, our frosted distance was 5.6 nanometer. So R0 is equal to 5.6 nanometer. So R is equal to 1 by E is 0.99 minus 1 the whole raised to 1 by 6 into R0. R0 is 5.6 nanometer. So let's calculate that. 1 divided by 0.99 is 1.01 minus 1 whole raised to 1 by 6 into 5.6 nanometers. This is equal to 0.464 1 into 5.6. So this is 2.598 nanometers. But this is sort of unusual because I think there is some problem with my calculation. Um, yeah, there is some problem with my calculation. Isn't not sure whether it is the problem with my calculator because so I think this should be fine because we had seen in the last class that when E is equal to 0.98, the R is equal to 0.5 R0. I think we are almost matching that condition, right? In the previous problem solving session, in one of the questions, we have solved this. When thread efficiency is equal to 0.98, R is equal to the distance between the donor and the acceptor is going to is going to be 0.5 R0. And here we have the E something at 0.99 and you see the R value to be 2.55 nanometer, which is sort of like around half of your frosted distance or slightly less than your frosted half of frosted distance. Half of 5.6 is around 2.8 and this is slightly less than that, which is around 2.6 nanometer, right? So that's because your the fret efficiency is around 0.99. I think we are in a good place. This answer is correct. So if we have given what is the fluorescence lifetime in the presence and the absence of the acceptor, donor fluorescence lifetime in the presence and the absence of the acceptor, we can find out what is the distance between the pairs, and this is also one way to find out what is the distance between the pairs if we by measuring the fluorescence lifetime of the donor and the acceptor. Okay, So, so we we had seen one of the methods using which you can measure the fluorescence lifetime to be time correlated single photon counting, and in this part we can there is one particular question that we need to discuss in today's session. So it is to find what is the fractional intensity of components of tryptophan intensity decay. So at pH 7, the tryptophan displays a double exponential intensity decay. So yeah, so we know that fluorescence intensity decay follows a single exponential follows a single exponential curve where I of t is equal to I0 e raised to minus some k t. When you have more than one fluorophore, you will have contributions from the two fluorophores that those are involved in the decay. So you will have I of t is, you will have multi-exponential decay which follows this particular equation. I of t is equal to I0 summation of I is equal to 1 to n alpha I raised to minus t by tau I, where 1 by tau I is equal to ki. Ki is the fluorescence decay rate. And yeah, and you can see that there is a pre-exponential factor which is alpha I, and which depends upon the uh, counts of, which depends upon the number of how much the molecule is contributing towards the fluorescence intensity. It depends upon the concentration and the fluorescence quantity. And in case if if you have more than one fluorophore, for example, in a protein molecule, if you have like more than one tryptophans, which fluorescent, which is a fluorophore, which is present in protein. If you have more than one fluorophore in the protein, um, if it is the same fluorophore, which is tryptophan in this particular case, the pre-exponential factor depends upon the merely depends upon the concentration, and yeah, it exhibits, and the fluorescence quantity can also be affected by the environment environment at which the molecule is in. So in case if a tryptophan is inside the, if it is sort of, yeah, so if it is inside if it is inside a uh, if it has a different sort of an environment, it can provide different of the it can contribute differently to the towards the fluorescence, steady state fluorescence intensity. So if you look at the double exponential decay that the protein for that the tryptophan displays, um, it follows I of t is equal to 0.19 exp minus t by 0.62 ns plus 0.181 exp minus t by 3.33 ns, which means t is in nanoseconds. So what is the fractional contribution of 0.62 nanoseconds component to the steady state, like steady state intensity at 320 nanometer emission? So fractional contribution can be calculated as Fi is equal to alpha I uh, alpha I tau I divided by summation of alpha I tau. So in this particular case, we know that alpha 1 is 0.19, this one, right? This is the pre-exponential factor, and tau I is the denominator in the exponential. So tau 1 is equal to 0.62 nanoseconds. Alpha 2 is equal to 0.81, which is given here. Tau 2 is the denominator of the exponential, denominator in the exponential, which is 3.33 nanoseconds. So fractional contribution by 0.62 nanoseconds subunit is equal to F. It corresponds to this particular component, which is F1, is equal to alpha 1 tau 1 divided by alpha 1 tau 1 plus alpha 2 tau 2. This is equal to 0.19 into 0.62 divided by 0.19 into 0.62 plus 0.81 into 3.33. This is equal to 0.19 into 0.62, sorry, 0.1178. So the denominator is coming to us 2.8. It's coming to us 2.8151. So this is 0.1178 divided by 2.8151. This is 0.04. So the fractional contribution by this component is 0.041 towards the steady state intensity. So the second question for this TCS PSC is, suppose we have two compounds with which is having equal quantities but different lifetimes. With tau 1 is 0.1 microseconds and tau 2 is 1 nanosecond. The solution contains equimolar of both fluorophores. What is the fractional intensity of each fluorophore? So the alpha 1 in this particular case is going to be alpha 1 and alpha 2 is going to be 0.5 because concentrations and quantum yields are equal. So if we have to find what is the fractional intensity, F1 is equal to alpha 1 tau 1 plus alpha 2 tau 2 plus alpha 1 tau 1 plus alpha 2 tau 2. So this is equal to tau 1 is 1 microseconds. This is 1000 nanoseconds. Tau 2 is 1 nanoseconds. So tau 1 is 0.5 into 1000 divided by 0.5 into 1000 plus 0.5 into 1. So this is going to be this is going to be 0.5 into 1000 is 500 divided by 500 plus 0.5. So this is almost 500 divided by 500.5. It's 0.99. Okay. And fractional intensity for the second fluorophore, which has the fluorescence lifetime of 1 nanoseconds, 0.5 into 1 alpha 2. So this is going to be, so F2 is equal to alpha 2 tau 2 divided by alpha 1 tau 1 plus alpha 2 tau 2. This is equal to um, 0.5 into 1 divided by 0.5 into 1000 plus 0.5 into 1. So this is 0.5 divided by 500.5. So this is equal to 0.00099. Okay, so this is how we can approximate this as 0.999, this to be 0.001. So this is going to be the fractional contribution of these two different fluorophores towards the steady state intensity given different lifetimes, and if both of them have mixed equimolar to the equimolar in a solution. Yeah. These are a couple of instances where we can use fluorescence to study different real problems. So here we have been given a protein that consists of a single subunit, and it has a molecular weight of 25,000 daltons, which is 25 kilodaltons. And the protein contains a single tryptophan residue near to the central core of the protein and several tyrosine residues, and the protein contains a single reactive sulfhydryl residue on the surface. So consider this to be our protein, and we have a tryptophan over here, and we have lot of tyrosine molecules. For example, yeah, we have lot of several tyrosine residues. Since the predominant fluorescence is being contributed by the tryptophan, you will see predominantly the fluorescence by the tryptophan. Then you have a sulfhydryl peak on the surface. So you have a sulfhydryl residue on the surface. Sulfhydryl means an SH group, which is a sulfur attached to a proton. So there is a monomeric subunit which forms the protein, which has a sulfhydryl group, which is cysteine. A cysteine amino acid in the protein have a sulfhydryl group. So the sulfhydryl group present on the surface of the protein. Okay. So now that we have to assume the monomeric protein can be unfolded by addition of a denaturant, and explain how the fluorescence spectral properties of the unmodified protein can be used to follow the unfolding process. So in this particular case, you have to use an unmodified protein, which means you are not supposed to tag the protein with any other fluorescent label. So how can we study the uh, the uh, the uh, the unfolding of this monomeric protein? So, what do you think about it? Do you have any particular idea of how the protein, how the fluorescence signature of the protein will change depending upon whether it is folded or unfolded? So there have been a lot of studies that has been done, and there has been like we have been covered a couple of those things in the class. So that is by finding the stock shift and decrease in fluorescence intensity. So this is a fluorescence spectrum of RNAs, which is a protein. This is just an instance. The protein that is mentioned in the question doesn't have to be RNAs for sure. This is I'm just giving an instance where people have studied fluorescence, the unfolding using fluorescence. So here, what you can see is there is a uh, this is the fluorescence spectrum of RNAs at different conditions. The one in this particular, the one that I'm pointing now, The one that I'm pointing now here is the one which is at 20 degrees Celsius. As we increase the temperature, the protein can unfold. So you can see at 50 degrees Celsius, which is in this color, which is labeled as 2, you can see that the fluorescence intensity has reduced, but we don't see a tremendous shift in the peak position. But when you go to 65 degrees Celsius, which is which is labeled as 5 here, sorry, which is labeled as blue here, which is labeled in blue and as a label of 3 here, you can see that there is a steep decrease in fluorescence intensity along with a slight shift in the peak, right? So this says that when it is folded, the tryptophan is inside the hydrophobic core of the protein, and when you unfold the protein will become something like this, and your tryptophan being exposed to polar environment of water. So you'll have like water around it. So you have like water around it. So here it was in hydrophobic. This was inside hydrophobic core. Here it is in a polar environment. Because of which you will sort of see a decrease in fluorescence intensity along with the stock shift. The other two graphs shows with, so this is at 20 degrees Celsius with no in native condition. When you add a denaturant, which is here it is in guanidine hydrochloride with 4.5 molar guanidine hydrochloride, you can see that there is a drop in fluorescence intensity, and as we don't see a very steep shift in the exciting emission maxima, but when you come to 7 molar guanidine chloride, you can see this is a denaturant. You can see that the peak has have had a excitation maximum have had a stock shift along with the strong diminution in the fluorescence intensity. So this suggests that by following the stock shift and the decrease in fluorescence intensity, you will be able to follow the protein denaturation. So if you, with the denaturant concentration versus the or you with the denaturant concentration versus the fluorescence intensity, normalized fluorescence intensity, you can sort of get a plot like this from which you can calculate the fluorescent you can calculate the you can calculate the you can follow the unfolding process. In class, I think sir has mentioned about different how the how we can fit this data set to a particular equation. So here, this is just a representative figure how the peak maxima changes depending upon the environment of tryptophan inside the protein. So this is the one in the indigo color is for the protein which is very much in a hydrophobic core, and it has an emission maxima at around uh, 310 nanometer, and you can see that the emission maximum is shifting to 320 nanometer when you have a slightly exposed tryptophan, which is like, so we are moving from a very hydrophobic core which is denoted, so we are moving from very hydrophobic core which is denoted here to something like this, which is not a very much hydrophobic, but it has it has moved out from the very much hydrophobic core to a slightly hydrophobic core. When you come to third for the emission spectrum of the third protein, for the tryptophan attached to this third protein, it is slightly it is sort of like in the surface of the protein where it forms some sort of interactions with other amino acids. It can be due to some other hydrophobic interactions, whereas it has some it has a surface some surface which faces towards the polar environment. So that's why you again see a stock shift of the emission maxima. And when it is like completely unfolded, when it just have only polar environment out towards it, which is in case of this fourth um, tryptophan, for tryptophan labeled in yellow. You can see a completely stock shifted. Uh, Stock shifted emission maxima. So this is this is one of the method by which you can follow the tryptophan fluorescence to get some insights about the protein unfolding process. Uh, so the second part is uh, is to describe the use of conditional quenchers to probe the accessibility of tryptophan residues to the solvent. So I think we had been shown how the how the quenchers are going to affect the uh, affect the fluorescence of a fluorescence of a fluorescent molecule. So in this is one of those examples where the tryptophan, this is a molecule which is called endo-3. I forgot what is its use, and it has two tryptophan residues. One is sort of like slightly buried, one is like very much exposed, and you can see that how the fluorescence follow the fluorescence of endonuclease 3 upon different concentrations of quenchers which they have used as iodate ions as the quencher, and you can see that uh, it is not going towards a smooth straight line. It is sort of going to uh, have contributions from two different tryptophan residues, and by following this and fitting this to a Stern-Volmer equation, you will be able to find out um, what is the surface accessibility of the tryptophan residue to the solvent. So this is one of the methods that you can use to find the surface accessibility of tryptophan residue to the solvent or to any other quenchers in the conditional quenchers in the solvent. The third sort of a real problem is to assume that the unmodified protein associates with another subunit to form a dimer, and how could the fluorescence to be used to follow this association process. So you have yeah, let me first explain this. So we have the protein, and you have one more of it, and you want to find how it associates. Okay, sort of like this. So in this particular case, you just have one molecule, right? And here it is like a single. So this is a 25 kilodalton, 25 kilodalton protein. This is a 50 kilodalton. So you can use sort of sorry, you can use fluorescence lifetime to follow this particular association process. So this is one reason why we can't use FRET or any other processes. You have to use an unmodified protein. So this is an example. This is an example where people have followed the self-association or dimerization of a protein. So this is a interferon gamma dimer. So it has some one tryptophan and four tyrosines, and you can see that the tryptophan is inside the deeply inside the protein, whereas the tyrosine residues are unevenly distributed across the protein. And you can see that, yeah. So this is the fluorescence emission spectrum of this is the fluorescence emission spectrum of the dimer, and this is the one for the monomer. So you can see that the emission spectrum of dimer is much more higher than the emission spectrum of the monomer, and yeah, because of different lifetimes of dimer and the monomer, it in turn affects the steady state fluorescence intensity. So you can sort of yeah, we can sort of follow the process by measuring the fluorescence lifetime. So if you are sort of like a following a mixture, we know that I of t is equal to, if you have two sets of conformations or two sets of different different conformations of the same molecule, you can have two sets of fluorescence. You can have two different fluorescent lifetimes, which is tau 1, this one continues to tau 2, and you can follow alpha IC1 to alpha 1 tau 1 plus alpha 2 tau 2. And by if we know the inherent lifetimes of these two molecules, we will be able to find what is the, from alpha 1 and alpha 2, we will be able to calculate what is the concentrations of dimer and monomer, using which you can follow the dimerization process. Yeah. The next one is to how can we use the fluorescence spectroscopy to measure the distance between tryptophan residue and the reactive sulfhydryl group. Um, so, so yeah, our molecule was something like this, and we have a tryptophan here, and you have a couple of tyrosines, and you have a SH group on this surface. So what you can do is you can modify this SH. You can modify this SH to one of the fluorophore. For example, there is one like dancide chloride. There is one other like fluorescein. I forgot its spelling. Yeah, you can label the fluorescent molecule. Label with the fluorescent. Yeah, label this SH with the fluorescent molecule like dancide chloride or fluorescein, and you can perform FRET experiment. So you know what is the Foster distance between the tryptophan and the fluorescent molecule that you are labeling the sulfhydryl group, and yeah, instead of this H you will have a fluorescent molecule maybe. I should just mention. So once you label it, it will be something different, and you will yeah, what you can do is you can then perform the FRET experiment to find the distance between these two residues. So we can use FRET and label with the fluorescent molecule and perform FRET experiment. So this is one of the example where they have done. Um, so they have a um, they have a alipoprotein apo2, and it sort of have two different. It can sort of adopt two different conformations where the two sites where it have the donor and the acceptor close, and where the donor and the acceptor too far away. And you can see that when the donor and the acceptor are so close, you can see that the fluorescence intensity is going down, and when it is not, when both of them are far apart, the decrease in fluorescent intensity is not as much as when it was close. So yeah, uh, so you can basically you have to label the protein with a fluorescent molecule and perform FRET to find the distance between the ways. The last part is how to use the energy transfer to measure the self-association of the protein after the protein has been modified with sulfhydryl group dancing chloride. So this is again sort of like how to find the self-association property. So you have two monomers and you have tryptophan at the middle, and you have a sulfhydryl group at the side, and you modified it with dancing chloride. And what can we do to measure the how to use the energy transfer to measure the self association after the protein has been modified with sulfhydryl groups. So one thing that we can do is uh, Yeah, in terms of energy transfer, it should happen between the tryptophan to this SH until and unless there is sort of like more closer association. There you have like the protein and you have the other protein and you have tryptophans in the middle and you have an SH. So you have the SH and which is very close to the tryptophan of the other monomers. In this particular case, there can be a Fred transfer from the sulfhydryl group attached to dancyl chloride to the tryptophan of the nearby residue. The other way is you can differentially label these two residues. Basically, what you can do is one can be dancyl chloride, the other can be fluorescein, for which you know what is the um, yeah, for which you know what is the uh, donor acceptor frosted distance, and using which you can calculate what is the distance between the fluorescent these two fluorescent molecules. Yeah, I know last set of the problems was little lengthy. Yeah, I just thought of explaining it to you in case you're sort of interested. There was a question about green fluorescent process in last lecture. There is, as far as I could find, there is nothing like green fluorescent process. Um, there is only some. There is only something like green fluorescent protein. So um, these are something which is present in, yeah, something which is present in proteins, which is sort of modified by itself to form a fluorescent molecule inside the proteins, which in turns make the protein fluoresces by itself, apart from the tryptophan fluorescence. So yeah, I'm not going much into detail as it is sort of like out of the scope of the course that we are dealing with. I don't know whether Sir has mentioned it in the microscopy part. Yeah, maybe we'll go over it in the next lecture. Um, yeah, if you have any particular questions about the problems that we have discussed, please let me know. I'll be happy to answer. Yeah. Today we have in the first part we have sort of covered how we can calculate the fluorescence lifetime, and yeah, and if we have given how fluorescence lifetime, how to calculate the distance between the donor and the acceptor in case of red pair, and we have also calculated how calculate the calculated the fractional contribution to steady state densities. Yeah, then the second part of the problems was second part was about a protein association unfolding. How can we follow protein association and unfolding using fluorescence? Uh, Please let me know if you have any particular questions from the part that we have discussed. Yeah, I I don't see any hands raising or any questions in the chat box. If you don't have any particular question, uh, yeah, let's end the session for today. Thank you all for joining. Thank you very much.